Okay, this is Tech Math 4, and we're in section 28.5, which has to do with Maclaurin series. Probably some Scotch guy. What do you think? And his series is going to be fabricated. F of x is going to be equal to the function at 0 plus the first derivative of the function times x divided by, this is really divided by 0 factorial, and that's divided by 1 factorial. 0 factorial is 1 and 1 factorial is 1, plus f double prime at 0 divided by 2 factorial x squared plus blah 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 plus f the nth derivative at 0 x to the n divided by n factorial, and then this goes on forever and ever and ever. So we could have written it, if we wanted to, summation n equals 0 to infinity f n derivative, so the 0th derivative would be no derivative at all, at 0 divided by n factorial x to the n, so we could write it that way. So this is an expansion around the point x is equal to 0, because we're finding the derivatives and the functions at 0. So it might not work at x equal to 75 million. It probably won't, but that'll be the case. All right, so that's the theory of the situation. So now we're going to work over to the problems, and the number one problem is number 1. So we'll look at number 1, and we want to find the Maclaurin expansion of sine. So I find f of x is equal to sine x. I'm going to find f at 0. Find that to be 0. F prime at x turns out to be cosine x. F prime at 0 is 1. And I'm going to find f triple prime, double prime of x, which is going to be minus sine x, and then f double prime at 0. And I'm going to have 0, and then f triple prime x is equal to minus cosine x. F triple prime at 0 is minus 1. And then I start all over again, because the 4th derivative will be sine, the sine will be 0, the 5th derivative will be cosine, the cosine at 0 will be 1, and then I end up doing the whole thing over again. So that being the case, the function sine x has a series expansion, and that series expansion is 0, which I won't write down, plus 1x minus, and that's 1 over divided by 1 factorial, which is a 1. We normally don't write it. X cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus blah 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 blah, and then it would continue on. So I only have odd exponents of x because the even guys are 0, and that's what it would look like. So I would write that as x is equal to minus x cubed over 3 factorial plus x5, x to the 5th over 5 factorial minus x to the 7th over 7 factorial, x to the 9th over 9 factorial, minus x to the 11th over 11 factorial. What's 11 factorial? Anybody know? 11 factorial. 39,916,800. So that's a huge number. So this term isn't worth much. This does not work in degrees. So if I wanted to know what the sine of 90 degrees is, and it's supposed to be 1, and I put a 90 in there, I wouldn't get the right answer. This is a radians only thing. So that'd be the sine of pi over 2. So if I put pi over 2 in there, I should get 1. Okay, so I'm going to put pi over 2 over there. So I got pi divided by 2 minus pi divided by 2 cubed divided by 3 factorial, which is 6. Well, I'll just put in 3 factorial. And I'll hit the enter key. So with 2 terms, I get a 0.92. Now I'm going to add the third term plus pi over 2 raised to the 5th power divided by 5 factorial, and I get a 1.0045. If I take the minus term, I'm going to get rid of some of that and be closer. By the time I get to the 4th or 5th term here, I'm going to get so close to 1, I'm going to know that I'm there. And this guy here is so small that it's not going to make much difference anyway. So when your calculator, when you go in your calculator and say, I want the sine of 45 degrees, it doesn't go to a lookup table. What it does is it executes this function to the number of things that it needs to get the degree of accuracy that it wants. So your calculator is going to give you 10 digits. It probably only has to do 5 of these, 5 or 6 of them to have 10 digits of accuracy. It would change your degrees to radians before I put it in, but that's what it's calculating. So I put in 57.7839 and hit the sign button. I even knew where the sign button was on my calculator. Sign 52. Blah 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 boom boom boom. It comes up with that answer right away, 0.792. But that's what it used. It used a series approximation to find it, and because you don't need 30 digits of accuracy, it can do it very quickly. Okay, so that's number 1. Next guy is number 16. No, it's not. Number 10. All right, so number 10 is x sine to the x. Oh boy. So f of x is equal to x sine x. Okay, now when I get done, I know what sine x is, right? So I had better get x squared minus x to the 4th over 3 factorial plus x to the 6th over 5 factorial minus x to the 7th over x to the 8th over 8 factorial. That had better be my answer when I get done, right? Because if I take the sine x from the other guy and I just multiply them by x, so I multiply this guy by x, that's what I'm going to get. So I know the right answer. Now I'm going to have to, in fact, I'd probably just do that, you know. But because I'm in this thing, we're gonna do it the hard way, so to speak. So I'm going to find f at 0, which is going to be 0, and then I'm going to find f prime of x, which is going to be sine x plus x cosine x, and I'm going to find f prime at 0, and I'm going to find that that's 0. Well, that's good because I don't have a unit term and I don't have an x term. So to have both of those guys be 0 is okay. And I got f double prime of x, and I'm going to have cosine x plus cosine x minus x sine x. And I'm going to have f double prime at 0 is going to be 2. I come up here, and yeah, if it's 2 divided by 2, then that's going to be a 1. Alright, so far I haven't made any mistakes, so that's good. So f triple prime at x is minus sine x minus sine x minus sine x minus x cosine x, and f triple prime at 0 is 0. All those guys are 0. That's fine. f, the fourth derivative, is going to be minus cosine, minus cosine, minus another cosine, minus another cosine, plus x sine x. So the fourth derivative at 0 is going to be minus 4. Okay, is minus 4 right? When we come back up, then, yeah, minus 4, this would be minus 4. I don't know if minus 4 is right or not. Minus 4. But why would that be? What is that? That's the fourth derivative? Okay, well, the fourth derivative would be divided by 4 factorial, so minus 4 divided by 4 factorial is something divided by 3 factorial, so that's right. So my first two terms are correct, and I could do it 2 more times and see if I can get the last guy right, but I'm not gonna. I'm going to say that it's going to work, and that my function x sine, is that what it is, x sine x, is going to equal x squared minus x to the fourth over 3 factorial plus x to the 6th over 5 factorial minus x to the 7th over 8th over 7 factorial plus x to the 10th over 9 factorial, blah, blah, blah. All right, so that worked out okay. Number 13. Wants us to do the sine of x minus pi over 2. Okay, so f of x is equal to the sine of x minus pi over 2. Let's see, now if x were pi over 2, that looks like minus cosine is what it looks like. Anyway, it doesn't really matter. What matters is that we're going to solve it. All right, so f at 0. So the sine of minus pi over 2 would be minus 1. F prime x. Cosine x minus pi over 2 times the derivative of the argument, which is 1. F prime at 0 is cosine of minus pi over 2 is 0. Okay, F double prime x minus sine x minus pi over 2, and f double prime at 0, the sine of minus 90 degrees is minus 1, minus that would be 1. F triple prime x minus cosine 1 x minus pi over 2. F triple prime at 0 is 0, and the fourth derivative at 0 is going to go back to be what the 0th derivative was, which was minus 1 again. All right, so we're going minus 1, 0, 1, minus 1. Okay, so the 13, the sine x minus pi over 2 is going to give me minus x divided by 1 factorial, which I'm not writing, plus x cubed over minus x cubed over 3 factorial minus x5 over 5 factorial plus x7 over 7 factorial. Why do I not like this? Because it's wrong. Yeah, that's why I don't like it. There, that's better. So minus 1, there's no x associated with that, with the 0th derivative. So it's minus 1 plus x squared over 2 minus x to the 4th over 4 factorial plus x to the 6th over 6 factorial minus x to the 8th over 8 factorial. And even though we don't know what the cosine function is, this is the same as minus the cosine function of x, which is what we thought it was going to be anyway. On the bottom of page 973, we see that the cosine function of x is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus blah, blah, blah. So we know that even though we don't know that yet. Okay, number 18, and then we get to move on. What a bummer. Who thought of doing that? Okay, so f of x is 2x minus 1 raised to the 4th power. Right, now, on the side here, if I do Pascal's triangle, I get this, right? And so this had better be 2x to the 4th minus 4 times 2x cubed times 1 plus 6 times 2x squared minus 4 2x plus 1. That's what I'd better get when I get done. If I don't have that doing what I'm doing, then there's something wrong, because I know the series expansion of 2x minus 1 to the 4th power. I can see it. All right, so now I know that, but we're in a different chapter. So I'm going to look at this guy, and that's going to be 1. F at 0 is going to be 1, and there's my 1 sitting right there. I can see it. Okay, so that's good. F prime at x prime of 0, x. Okay, so I'm going to go, the 4 goes out in front, 2x minus 1 cubed times the derivative of the inside, 2x. So I'm going to have 8x times 2x minus 1 cubed. Very interesting. F prime at 0 is minus 1. Somehow I don't think that works. What did I do the derivative wrong? 4 at 2x cubed times, times 2, not 2x, you idiot. So yes, I did the derivative wrong. X cubed times 2, which gives me 8, 2x minus 1 cubed. And now at 0, I end up with an 8. No, I can't end up with minus 8. Minus 8. I look there, what do I see? Minus 8 divided by 1, right? Okay, so that's good. F double prime of x. 24, 2x minus 1 raised to the 2nd times 2, 48, 2x minus 1 squared. F double prime at 0 is equal to 48. F triple prime x equals 96, 2x minus 1 raised to the 1st times 2, 192, 2x minus 1 raised to the 1st. F triple prime at 0 is minus 192. F, the fourth derivative, x, is equal to 384. Okay, and then the next guy is going to be 0, so there are no more after that. So that being the case, f, the function f of x would be 1 plus 1 minus 8. 1 minus 8x plus 48x squared over 2 minus 192x cubed over 3 factorial plus 384x to the fourth over 4 factorial. And that would be 1 minus 8x plus 2 goes into there, 24, 24x squared times 6 goes into there 32 times x cubed, and 12 that'd be 4 factorial is 12, I think. 384 divided by 4 factorial. 16 x to the fourth. Okay, so I remember what that guy looks like, and I move back up to my Pascal's triangle thing, and I had 16x squared minus 32x cubed plus 24x minus 8x plus 1. So I get the same thing as I did it with Pascal's triangle. Both ways I got the same answer. So that's convenient. You know, math is supposed to, if I do it different ways, I'm supposed to get the same answer.
Seems like the first way is easier.
It could be, but you'd have to remember to do it.
Yeah.
Yeah, and that would be the issue. Would you remember that the Pascal triangle answer is in fact a series approximation just as much as what we're doing is? But if you recognize that, then it would be simpler to do. Okay, we're ready to go to section 38.6, and now we're talking about a Taylor expansion. And for those with TI-86 calculators and better, you have a Taylor expansion function on the calculator. You just tell it to do it, and it expanded. And in fact, Taylor expansion with A equals 0 is the same as 36 full. The last section we did is the Maclaurin expansion. So there's no difference between Taylor's expansion at A equals 0 and the Maclaurin expansion at all. So the Taylor expansion says well, I guess we can't do that because that's really 38. Remember that that's the beginning argument for 38.7. Moving back to 38.6. 28.6. Moving back to 28.6. We're given the expansion for e to the x, sine x, cosine x, and natural log of x. They're given. And then we're going to use them to solve problems. All right. So we're going to start with number 1. And we want to find e to the minus x. Well, we know that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial. We know that we know that because it's given to us on the page before. So e to the minus x is just going to be 1 minus x plus x squared over 2 factorial minus x cubed over 3 factorial plus x4 over 4 factorial. And then I don't have to necessarily do the rest of the math. And so that was number 1. Next is number 14. So we want e to the x divided by x minus 1. E to the x divided by x minus 1. Oh, I don't know how I'd want to do that. It would seem like it'd be an easy way to do it. And all right. Well, I guess there isn't. I guess we'll just find f at 0 is minus 1. F prime of x. So this is e to the x times x minus 1 to the minus 1. So that's going to be e to the x, x minus 1 to the minus 1, minus e to the x, x minus 1 to the minus 2. Okay, f prime at 0. 1 minus 1 is 0. Okay, f double prime x. E to the x, x minus 1 to the minus 1, minus e to the x, x minus 1 minus 2, minus another e to the x, that guy, so that's going to be 2 of them, plus 2 e to the x, x minus 1 to the minus 3. Alright, so f double prime at 0, this is a 1, no, I'm going to have to go back and look at this for a moment. Minus 1, okay, so this is a minus 1, and this is a minus 1 squared, so it's not going to be 0, it's going to be minus 2. Okay, so here we got a minus 1, a minus 2, and a plus, and another minus 2. Okay, so this is minus 1, this is minus 2, and this guy's going to be another minus 2, so it looks like a minus 5. I predict, see, we've gone minus 2, minus 1, minus 5. I don't know. F triple prime x. E to the x, x minus 1 to the minus 1, minus 3 e to the x, x minus 1 to the minus 2, okay, plus 2 of them, plus another 2 of them, for e to the x, x minus 1 to the minus 3, minus 3, minus 6, e to the x, x minus 1 to the minus 4. Hope I did that right. F, the third derivative at 0. That's minus 1. This is minus 3. That's minus 4. That's minus 6. For a minus 14? I guess so. Alright, so I'm ready. Which one are we doing? We're doing e to the x divided by x minus 1 is going to be minus 1. Minus 1 minus 2x minus 5x squared over 2 factorial, which is really 2, minus 14x cubed over 3 factorial. Okay. Now we're going to check our work. E to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus x5 over 5 factorial. And I'm dividing by x minus 1. Okay, I'm going to rewrite that in a different order. I'm going to rewrite it as minus 1 plus x. Okay, so minus 1 goes into minus 1 times, and I get a minus 1 minus x. I subtract, I get 0. I subtract, I get 2x plus x squared over 2 factorial plus the other guy. That goes in there minus 2x times. Okay, so I got 2x minus 2x squared. Okay, that subtracts, I get 0. This is 1/2, that's 2, so that would be 5 halves. 5 halves x squared plus x cubed over 3 factorial. Okay, so minus 1 goes into there 5 minus 5 halves x squared. Okay, so this is going to be minus 5 x squared over 2. Okay, I'm going to have 5 over 2 x squared minus 5 over 2 x cubed. That guy goes away. Okay, so I got 1/6, because 3 factorial is 1/6. It doesn't look like a factorial, though, does it? There we go. So I got 1/6 plus 5, 1/6 plus 5 halves equals, change to a fraction. I got 8/3. So I've got 8/3 x cubed plus x to the 4th over 4 factorial. Okay, so this is going to go in minus 8/3 over x cubed. Minus 8/3 x cubed. And that's not a 14. Is my 14 wrong, or is my 8/3 wrong? One 1/6 plus 5 halves equals 8/3 is correct. Okay, now I look up here, and I'm taking the derivative of this guy. So I get that guy, I get minus 1 of this guy, giving me minus 3. I get a plus 4 with that guy sitting with the cubed. Okay, but then I've got another plus, so this is really not a 4, this is really a 6. Okay, so that's a 6, this is a 6, this is 16, that's 16, and if that's 16, that's minus 8 over 3, so now the problem checks. So now that checks, this checks. Are we done with this section yet? That was 18. We have to do 23. This is the reason 23. This is the reason we're doing series expansions. I need to evaluate the integral. Okay, so I'm going to take the integral from 0 to a half of the sine of t squared. Sine t squared. Okay, so that's what I'm being asked to evaluate. And I look in the back of the book to look up the integral of sine t squared. And I see it's not there. I don't have that integral. I'm hosed. But I also know that the series expansion of sine t is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. And I really don't need that many terms. It probably tells me how many I'm going to use. Find the Q in coulombs. Well, it doesn't tell me how many, but that's all I'm going to use, just those. And then I say, well, if the sine of t is this, then the sine of t squared has to be t squared minus t to the 6th over 3 factorial plus t to the 10th over 5 factorial minus t to the 14th over 6 factorial, 7 factorial, right? So now if I want the integral of this guy, 0 to a half, then I can just take the integral of this guy, 0 to a half. Okay, so I'm just going to use 4 terms. So I'm going to have t cubed over 3 minus t7 over 7 times 3 factorial plus t to the 11th over 11 times 5 factorial minus t to the 15th divided by 15 times 7 factorial, evaluated at 0 and a half. And I say, well, gee, t to the 1/2 is extremely small. When I divide it by that guy, t to the 11th is extremely small. In fact, I can probably get away with just the first stupid term here, right? So if I go 1/8 divided by 3, I end up with, just using the first term, 0.0416 repeating. And then if I subtract 0.5 raised to the 7th divided by 7 times 6, and I forgot to do that right, raised to the 7th divided by, what's 7 times 6? 42? 42. I end up with 0.04148. And if I add this itty-bitty thing, it's not going to make any difference, so I'm there. And if I only want 2 significant digits, there's nothing wrong with that answer, right? And it'd be coulombs because I'm doing an electrical problem. So I can use series expansion to solve integrals that I couldn't find in my integral table if I wanted to. I'd have to be wanting to a whole lot, but other than that. Okay, it is time to move on to 28.7, which is Taylor expansion, which is what I started to talk about before I realized I was in the wrong spot. So 28.7. So my Taylor expansion says my f of x expanded about a. So I'm not expanding around 0, I'm expanding about some other point. Now, why would it that I wouldn't want to expand around 0? 0 could be an undefined point. It could be infinity. So if I looked at something like tangent x, well, tangent x at 0 is 0 I wouldn't want to expand it there. Well, that would be okay. Tangent x would be okay. But cotangent x would not, because at cotangent x at 0 is infinity, right? So I wouldn't want to do it there. So I'd want to pick some other point to expand around. Pi over 2 would be a good spot, for example. So Taylor expansion is a more general expansion, and it says that my function is going to be the function at a plus the first derivative at a, x minus a, and this is divided by 0 factorial, this is divided by 1 factorial, we normally don't write them, plus the second derivative at a, x minus a squared over 2 factorial, plus blah 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 for the rest of it. So we're doing a more general expansion around some point that may not necessarily be 0. But if it is 0, I can still use Taylor expansion because it'd be perfectly okay to do. Alright, so that's what I'm going to do. And I'm going to do problem number 1. And problem number 1 says a is equal to pi over 2. And f of x is cosine x. So we're going to find f of a, and that's going to be 0. The cosine of 90 degrees is 0. F prime x is minus sine x. F prime at pi over 2 is going to be minus 1. And then f double prime x is going to be minus cosine. F double prime at pi over 2 is going to be 0. F triple prime x is going to be sine x. F triple prime pi over 2 is 1. So my series expansion of cosine x about the point a is equal to pi over 2 is going to equal 0 minus 1 over 1 factorial x minus pi over 2 plus the squared term goes away, 1 over 3 factorial x minus pi over 2 cubed minus 1 over 5 factorial x minus pi over 2 to the 5th. And then I'll throw in another term plus 1 over 7 factorial x minus pi over 2 to the 7th. Minus, and I continue on the same pattern. Oh, look at this. We're supposed to do the midterm today, so if I finish the next 2 sections, we can do the midterm. Wouldn't that be great? Huh?
Oh, fantastic.
We could probably get it done today. I
Class?
guess not, huh? No, I'm losing my voice. We're not going to do it today. Was that 1? Okay, number 5. I think what we'll do, Control Alt F. Okay, so number 5, we have the square, f of x is the square root of x. And we want to do an expansion around 9. A is equal to 9. Alright, so we want f of 9, which appears to be 3. And then we want f prime of x. So this is x to the 1/2, so it'd be 1/2 x to the minus 1/2. F prime at 9 would be 1 over 6. F double prime x would be minus 1/4 x to the minus 3/2. Minus 3/2. So I got to subtract 1 from 1/2. F double prime at 9. Okay, so that'd be minus 1 over, I've got a 4, and I've got the square root of 9, which is 3, and then I got 3 cubed, which would be 27 times 27, minus 1 over 128, 108, 108, 108. F triple prime x, this is going to be a positive 3 over 8 x to the minus 5 over 2. F triple prime 9, so that would be 3 divided by 8 times 3 to the 5th. Okay, so that made 3 to the 4th, so that's 81 times 8, 648, 1 over 648, I think. So f of x would be 3 plus 1/6 x over 1 factorial minus 108 x squared over 2 factorial plus 1 over 648 x cubed over 3 factorial. Okay, there we go, and we'd probably, I don't know what we'd do with that. We'd probably just leave it that way. That's probably what I would do. We're in 7, so I did, that was 5?
Yep.
Okay, so we're going to do 12 next. Number 12. F of x equals 1 over 1 minus or plus 2x. A is equal to 1. So f at 1 is 1/3. F prime x minus 1 minus 2x to the minus 2. F prime at 1 minus 1/2. 1 goes in here, that makes it a minus 2, a minus 1. Minus 1 squared gives me plus 1, minus, but it's on the bottom. Okay. F double prime x 2. Oh, bummer. Get rid of that, get rid of that, get rid of this. Okay, I go and I put the minus 1 out in front, I make it minus 2, but I still have to take the derivative of the inside, which gives me a plus, which gives me a minus 2, so this becomes plus 2, and at 1, I'm going to get 1. Okay, so that's better. Now I'm going to get minus 4 times another minus 2, which would be 8. I'm going to get 8. 1 minus 2x to the minus 3. Okay. F double prime at 1. 8 divided by minus 1/8. Minus 8 plus 8. Minus 8. I'm going to go with minus 8. And I'm going to come back here and say this is plus 2. because this is a 1, that's a minus 1, that makes that a plus 2. Okay, that's a 1, it's a minus sign, it keeps the minus sign, minus 8. Okay, one more. F triple prime x minus 24 minus another 2 gives me 48. 1 minus 2x to the minus 4. F triple prime at 1 going to be 48. Alright, so that being the case, f of x will be, was it 1? 1/3. 1/3 plus 2x minus 1. And this is divided by 0 factorial divided by 1 factorial. We're just not writing it down. Minus 8 x minus 1 squared over 2 factorial plus 48 x minus 1 cubed over 3 factorial. Okay, so I'm gonna rewrite it as 1/3 plus 2 x minus 1 minus 4 x minus 1 squared plus 6 goes into 48 8 times 8 x minus 1 cubed minus blah blah blah. We have more, but we're not working them out. Was that the last one? No, one more to go. 15. No, one more to go. 15. Number 15. F of x is cosine. And a is equal to pi. All right, so f at pi is minus 1. F prime x is minus sign. F prime at pi is 0. F double prime x is minus cosine. X minus at F double prime at pi minus plus 1. Plus 1, because cosine pi is minus 1 minus minus 1 is plus 1. F triple prime x sine x. F triple prime pi is 0, and then we repeat ourselves. Okay, so now cosine x at a is equal to pi is going to be minus 1 plus x minus pi squared how can that be? Something's not right. Oh, yeah, that's right. Yeah, everything's fine. The cube guy, okay, minus x minus pi to the 4th over 4 factorial. This is over 2 factorial plus x minus pi to the 6th over 6 factorial minus x minus pi to the 8th over 8 factorial. And this guy's over 0 factorial, but we normally don't write it. Okay, so we're done with section 28.7. Now the issue is, should we do section 28.8? And the answer is yes, we probably should. Yes, Mr. Conrad? Yeah, what's the question?
Okay.
Yeah, Control, Alt, Okay, so we're back on, and we're doing 28.8, section 28.8, and this is computations using what we've known so far. All right, so 28.8, we're going to do number 1, and we want to find e to the 0.1. Now, of course, we're going to take our calculator and go 0.1. Let's see, I think, where's the on button? Okay, there's e raised to the 0.1, and I better get an answer of 1.105170918. That's what I'm looking for, something like that. Okay, but e to the x series expansion is 1 plus x squared over 2 plus x cubed over 3 factorial, and it says to use the first 4 terms. Okay, so we want to go 1 plus 0.1 plus 0.01 over 2 plus 0.001 over 6. So we'll do that computation and see what it comes up with. 1 plus 0.1 plus 0.01 divided by 2 plus 0.001 divided by 6. And my calculator says 1.10516 repeating, which rounds off pretty close right there, right? So it rounds off to the same answer. So I can find e to the x close to 0 by just taking a few terms, 4 terms, and that's what my calculator is doing, by the way. It's not looking it up, it's doing that series expansion for me. It's probably doing 10 terms of the series expansion to make sure it gets 10 significant digits, but it can do that very quickly, so that's not a real issue. Number 5, we want the natural log of a half. We don't remember the series expansion for that, but it's given to us someplace here.
Well, would you be able to just put that in your calculator?
Yeah, we will.
Oh.
But we have the natural log of 1 plus x as a series expansion of x minus x squared over 2 plus x to the cubed over 3 minus x to the 4th over 4. So we know that that's the expansion that we're dealing with. Again, we're using the first 4 non-zero terms. So in this case, if I want natural, first of all, we'll go natural log a half, put it in my calculator because that's what somebody wants me to do. And that would mean I'd have to know how. That's okay, you can want that. So my calculator says minus 0.693147181. Okay, so in this case, 1 minus x, 1 plus x is equal to 1/2. So x is equal to minus a half in my formula. So this is going to equal minus a half minus 1 over 8 plus 1 over 24 minus 1 over 64, I think. Okay, so minus 0.5 minus 1/8. No, I hit the wrong button. Minus 0.5 minus 1/8 plus 1 over 24 minus 1 divided by 64, and I end up with minus 59895888333. So I'm not very close yet, but these guys on the bottom are not getting smaller quickly. So it's easy to see that I am going to get that if I add a couple more terms, but I'm not going to because it only told me to use the first 4 terms. Number 9. wants e to the 1.3. So I find that in my calculator, so I know what it is. E to the 1.3, and I end up with 3.6692966668. And I'm going to do this e to the 1.3, and I'm going to do it with the first 4 terms. So I'm going to have a 1.3 plus 1.3 divided by 1 factorial plus 1.3 squared over 2 plus 1.3 cubed over 3 factorial. Okay, so that's what I'm going to do. 1.3 plus 1.3 plus 1.3 squared divided by 2 plus 1.3 cubed divided by 6. And I'm going to end up with 3.811166667. I messed something up. Because this can't be bigger than that guy. Because all these terms are positive.
Oh, they are.
Yeah, they're all positive.
Would the second one be 2 factorial?
No, this is 0 factorial. This would be 1. 2 factorial is 2.
Sorry.
I'm gonna put it in my calculator again. 1.3 plus 1.3 plus 1.3 squared divided by 2 plus 1.3 cubed divided by 6. Got the same answer. This is a mystery. Oh, maybe it's not. Maybe it's not a mystery. Yes, it is. E to the 1.3. All right, well, I did it.
4.3 to the 4th divided by 4 factorial.
0, 1, 2, but that's going to be a positive number.
Yeah, it has to be.
That's the problem. All these guys are positive.
So it keeps getting bigger.
I mean, wait a minute. Is it plus minus? Am I hosed? Is that what you're trying to tell me? No, it's all positive.
Yeah.
Yeah. Oh, I see the problem. Shit. It's not 1.3, it's 1. So I have that number, and so if I subtract 0.3, then I'm going to get 3.51116666667. So now, as I add more to it, I'm gonna get closer and closer to what I'm supposed to do. So it's not 1.3. It's 1 plus x over 1 factorial.
Okay.
All right, dumb me dumb. Number 13. Number 13. Okay, so this is find the value of the current with omega being that. Okay. So I is equal to sine omega t and omega t is equal to 0.3. So if I take my calculator and put it in radians, okay, so now I'm in radians, and I go sine 0.3, I end up with 0.2955 to 0.207. All right. The sine thing, sine x, is 1. Now it's x. X minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus x to the 9th over 9 factorial. Alright, that's what it is. So I'm going to do it with a 0.3. The sine of 0.3. Okay, so I'm going to have 0.3 minus 0.3 cubed divided by 6. Okay, so if I take the first two terms, I get 0.2955 plus 0.3 raised to the 5th divided by 5 factorial. If I take the, so this is 2 terms. If I take 3 terms, I get 0.29552025. That's with 3 terms. Okay, now I'm going to take the 4th term minus 0.3 raised to the 7th divided by 7 factorial. And when I take 4 terms, I get 0.295520207. So with 4 terms, I get the same answer as my calculator gave to me without doing the series expansion. And that's how the calculator can get that number so quickly.
I don't think this matters, but it should have been 0.03 instead of 0.3. It doesn't matter. You get the same.
Well, I'm going to get a different answer.
You get a different answer.
Yeah, but I'm going to do the same thing to get the different answer, right? Exactly.
Not a big deal.
Yeah, so I could go and put the right numbers in there, or I could not. But you're right. And it is the job of the front row to tell me I'm solving the wrong freaking problem. So,
See?
yeah.
I just waited until.
Just waited to the end.
Yeah.
What a pal.
So we
I
can
tell you.
pose over our fellow classmate.
Yeah, that's right. Hosed over.
Oh,
Control Alt